Okay. So in the simple harmonic motion, so we are talking about right now first about periodic motion. Any motion which repeats after your fixed interval of your time is called periodic motion. Is called as what? Periodic, or also called as of your harmonic motion, or called as of your periodic or your harmonic motion. The best example is your motion of your conical pendulum. Example is motion of conical pendulum. Conical pendulum. In uniform circular motion. In uniform circular motion like this. If this is your rigid body and here it is your spring and here bob has been attached. So it may go from one mean position to your extreme position. Again, this one like this. Okay, so this is your position. So right now, this is making an angle right now continuously. This is making an angle theta and this is making an angle theta. If it is a uniform motion, this distance will always be remaining for me the same, radius r, isn't it?
Yes, sir.
So this position is called as of your what? Mean position, and this position is called as of what? Extreme position. And if it is been moving in a circular path like this motion is also called as of your conical pendulum in uniform circular motion. Or one more example is a revolution of the earth around the sun. That is also a constant bit of
Yes, sir.
periodic motion, isn't it? So even you can take your revolution of earth,
Even rotation.
revolution of your earth around the sun, around the sun. Like say for example, this is your sun and this is your earth. So it is revolving around the sun in elliptical orbit. This is your earth and this is your sun, isn't it? So revolution of your earth, a revolution of your earth around your sun is also your periodic motion part. Around the sun,
Sir, can we consider
rotation
rotation of Earth also, sir, as periodic motion?
rotation of the earth on its own axis also
Yes,
we
sir.
can take it, no problem. We can also take of earth rotation of your earth about its own axis, about its own axis. That is also best example for your periodic motion. So the time interval after motion is repeated is called as of what beta? Time period. So one complete motion అయిపోయింది అనుకోండి, the time taken for making one complete revolution is called as of what right now for me? Time. So I can define here right now the time interval, the time interval after which the time interval after which the motion repeats, motion is repeated, motion is repeated is called time period, is called time period. Okay,
Yes, sir.
this is about your periodic motion. That is about your periodic motion. So what do you mean by periodic motion? But any motion which repeats after a fixed interval of a time is called as a periodic. The best example is motion of your conical pendulum in uniform circular motion. In uniform circular motion, or revolution of the earth around the sun, or rotation of the earth about its own axis part deflation is also the best example for periodic motion. And we are defining one important term here right now, beta. The time period or the time interval after which the motion is repeated is called as of what? Time period is called as of what? A time period part definition. Is it clear?
Yes, sir.
Next one is about your oscillatory motion. What do you mean by your oscillatory or your vibratory motion? Or your vibratory motion. Okay. So what do you mean by your oscillatory motion? Or what do you mean by your vibratory motion? So do you have any example? Do you have any idea, beta? Oscillatory means what? Vibratory motion means what? See, like assume like take a blade and keep in between your teeth and give a small jerk. What happened? It will be moving to
Yes,
and
sir.
fro about that one mean position, beta,
Yes, sir.
isn't it? So that is called as of your oscillatory or vibratory motion, like phone getting vibrated when it is in a
Yes,
vibrating
sir.
mode, isn't it? So if the periodic motion, if I'm taking right now, if
The
in
best is
periodic
scales,
motion.
like put a
Beta?
scale on table and
Yeah, even we can do like that. Keep a scale on your table and fix with one hand, and with another hand, if you give a small jerk, that will be oscillating at that position. So
yes,
if in a periodic motion, if in periodic motion, the particle moves back and forth, back and forth, back and forth means to and fro, beta, or we can say to and fro on the same path, on the same path, on the same path. The motion is said to be, the motion is said to be oscillatory. Okay, is said to be oscillatory or called as a your vibratory. Okay, so what do you mean by oscillatory motion, beta? If in the periodic motion, the particle moves back and forth or to and fro on the same path, on the same path, the motion is said to be an oscillatory motion or vibratory motion part. It is oscillatory motion is constrained periodic motion, beta. Can I say that oscillatory motion is nothing but of a form of a periodic motion only? Because it is
yes,
also
because
making the to and fro motion part oscillation. So I can say
yes,
that,
and in a particular period.
yeah, oscillatory is also the special case of your right now. I can say periodic motion. So I can say here right now, oscillatory motion, oscillatory motion is constrained, is constrained periodic motion, periodic motion between two fixed points, between two fixed points. So oscillatory motion is constrained. Constraint means it has to make the motion like that only. There is no other alternate. Constraint means restricted mode. In that mode
Yes,
only you need to move. So oscillatory motion is a constrained periodic motion between two fixed point part of relation. So you can say that periodic oscillatory motion is also a form of your periodic motion part of relation. Is it clear for everyone?
yes,
Is it clear, Beta? So that was about your definitions about your oscillatory motion and as well as of your periodic motion part of relation. So what is the difference between the simple harmonic, what do you call the periodic motion and oscillatory motion, Beta? In the periodic motion, the particle is making the to and fro motion. About what? About one fixed point. Whereas in the oscillatory motion part of relation, or we can say in the vibratory motion, it is making the to and fro motion about your mean position, right? Whatever the fixed point we are taking, back and forth, to and forth on the same path. The path is said to be an oscillatory or maybe your vibratory part of relation. So that is an oscillatory or maybe your vibratory motion part. Isn't clear?
yes, sir.
Now see, oscillatory motion may or may not be periodic motion, beta. Oscillatory motion may or may not be periodic. It's not a compulsory condition that it should be a periodic motion. So you can write that
Yes,
point right now here. Oscillatory motion, oscillatory motion, oscillatory motion may or may not be periodic, may or may not be your periodic motion. I'll tell you the examples for this. See, oscillatory motion may or may not have a fixed extreme points also, beta. Because if you take your scale and keep it your on your table and give a vibration, the first time when it goes to the upper position, the second time it may not go to the same position up,
yes.
isn't it?
Little
Now, after
less.
certain interval of a time, what happened?
It'll
It will
stop
come back
also.
to the rest position, isn't it? It
Yes,
will try to stop. So I can write, say, can say that oscillatory motion, oscillatory motion, oscillatory motion may or may not have, may or may not have fixed extreme points, may or may not have a fixed extreme points. Okay, so one more
yes,
point. Any oscillating body, or I can say that an oscillating body, an oscillating body moves, an oscillating body moves under the action of a restoring force. What do you mean by this one, beta? This is very, very important term. Restoring force. An oscillatory body moves under the action of restoring force. What do you mean by restoring? Some force is bringing the particle to back to the mean position. Okay, na?
Yes.
Let's say when you're oscillating the scale, keeping on that one, some force is again bringing it back to the mean position, again mean to your extreme position part. So restoring force is always acting. That means some backward force is always acting on that body. So that force is called as of what? Restoring force. That force is also called as what? Restoring force. An oscillating body moves under the action of what, beta? Restoring force. So I can say that an oscillating particle must must possess a stable equilibrium. Must possess a stable equilibrium. What do you mean by that one? If the particle need to be oscillate for a very long time, means there should be no external force acting on that body. If there is no restoring forces if there is no external forces acting on that body, that oscillating body will be oscillating for a very long time. So any oscillating particle must possess what type of an equilibrium, beta? It should be possessing your stable equilibrium. What do you mean by stable equilibrium, beta? I told you in work power energy. Like say if I take a ball in a if we take a like say small spherical ball, anything like this is in this one right now. Okay, so like this, in this one there is a ball. If I give a jerk, what happened? This ball will go up here right now,
Yes.
come back to the mean position, again go to the extreme position, again come back, and finally come back to the mean position again. Until finally,
Yes.
whatever was initial position, finally it will come back to the same position. That is called as of your stable equilibrium. So that is the reason I'm saying that an oscillating particle must possess what type of an equilibrium? It should possess your stable equilibrium. Is it clear, beta?
Yes.
Okay. So now I hope you got a clear picture about what do you mean by periodic motion and what do you mean by your oscillatory motion. So what do you mean by
Yes.
periodic motion? Means any motion which repeats after a fixed interval of a time is called as of a periodic or harmonic motion. Whereas in oscillatory motion, if in periodic motion the particle moves back and forth on the same path, then the motion is said to be an oscillatory motion or also called as of your vibratory motion part of relation. Some restoring force is acting on that body to bring back, so that restoring force is responsible for the oscillation. And in oscillating particle, what must be equilibrium, beta? It should always possess your stable equilibrium. Then only we can say that particle is undergoing what type of a motion? An oscillatory motion. Is it clear?
Yes.
Next one, actual our topic we are entering right now. That is about your simple harmonic motion. Simple harmonic motion. Simple harmonic motion. This is very important and a very big chapter also, beta. So please don't try to miss the classes and try to make your fundas very clear in this one, because we need a lot of applications of your rotational mechanics also, work power energy, and lot of kinematics is also involved in the simple harmonic motion, beta. So please try to go through each and every day class very neatly and try to do the numericals on this one very regularly. Very important topic and scoring topic also, beta, because it is also the basic for 4 5 chapters in the second year. Like in AC you have the application of simple harmonic motion, waves you have the simple harmonic motion application right now, wave optics we have the applications. At least for 3 4 chapters it is having the applications of this chapter in the second year, beta. Okay, so make your fundas
Yes.
very clear, and if you're having any doubts related to this topic, you try to clarify your doubts and make sure that you try to give a good working of time for the simple harmonic motion chapter. Okay, so now what is exactly simple harmonic motion? In shorter way we call as of your SHM. SHM. So it is nothing but of your, it is the simplest form of oscillatory motion, beta. The simplest form of your oscillatory motion is your simple harmonic motion. So I can say that SHM is the simplest form of what? Oscillatory motion. of your oscillatory motion. So the simplest form of your oscillatory motion we are going to study, that is called as of your simple harmonic motion. Now in oscillatory motion, what is happening beta? The particle moves to and fro from its mean position such that some restoring forces or torques are responsible for a body to bring back the particle to the mean position. Like take a simple pendulum. Take a simple pendulum right now. In the first case, what I did right now here. So when I'm taking the simple pendulum right now and moving it in a circular path, this is not a conical pendulum particulation. If I'm taking a simple pendulum right now here, like say this is your simple pendulum condition. So if I take a simple pendulum right now here, this is the mean position beta. This is the mean position of your simple pendulum, and here we are having a bob. When you take this to the extreme position right now here, what is happening? Some force is restoring it back, isn't it? So this is making an
Yes.
angle of your theta part deflation. So what is happening? The moment you take it to the upper portion, some force is again trying to bring back this body in the backward direction. What is that force? Can you tell me beta? See here. If in the equilibrium position, the forces acting on the body is right now, this is your m into g at highest position. Or when it is at the mean position, the forces acting on that body is nothing but of your mg here, and here there will be your tension T, isn't it? Now it is making an angle theta. So what is the path followed by this particle you see right now? The moment you're going from here, you're taking this particle from here to here. That means from the initial position, it has been raised to a height of your how much beta? H. It has been raised to a height of your H part affiliation. And this is say for example, actual length of your simple pendulum L part affiliation. Now can you tell me what will be the H beta? H will be equal to your how much for me? I told you already in the work over energy part of relation. So if I need to calculate this value of your H part, this is also L gada. From here to here also, this is also L beta.
Yes.
So now if I resolve this L, this will become how much for me? Or L cos theta here.
Yes.
This is your L beta. This is a
Yes.
theta. This is L cos theta. This is L sin theta.
Yes, sir.
So I'll try to write with other pen. From here to here, this will become for me how much? L cos
L
theta.
cost.
And here it will become for me L sin theta.
Sine.
Now I need the value of this H. This H means what? Capital L minus of your L into your cos theta. So that will be equal to your L into your 1 minus of your cos theta. So this is the height to which the pendulum might be, the bob might have been raised. Now in equilibrium position, and tell me what are the forces acting on that body beta? The one which is restoring this body back is like this. The another force is acting like this. If this is theta, this is also here theta na beta. So here this will be equal to how much beta? Mg into cos theta, and here it is nothing but mg into your sin theta. This mg sin theta is trying to pull back this body from the extreme position to the mean position. So this force is called as of what? Restoring force. Is it clear?
Yes.
అర్థమైందా మళ్ళీ చెప్పిన
Yes, sir. So
isn't
MG
it?
sin theta
Extreme
is
position,
pulling
what
the
is the force which is responsible for the particle to bring back beta? Mg sin.
sin theta.
Okay, so SHM is the simplest form of what? Oscillatory motion. Okay na beta?
Yes, sir.
In this motion, in this motion, particle moves, particle moves to and fro. Particle moves to and fro about its mean position. About its mean position. About its mean position, or we can say this is your equilibrium position. Okay, such that the restoring force, such that the restoring force or torque is proportional to the displacement, is proportional to what? Displacement from mean position, from your mean position. And this force will try to move only that distance from where you are trying to bring it back to the original position. So this restoring force will be directly proportional to the displacement, but in which direction beta? Opposite direction, because you are
Yes.
making the body to move in upward direction, and the displacement and the restoring force is trying to displace the body in the backward direction. So I can say that the restoring force or torque is proportional to the displacement from your mean position, and it is always directed away from where beta? Mean position, and is always directed directed towards what? Mean position. Towards mean position. Towards your mean position. So can I write restoring force is equals to how much better? Restoring force is equals to restoring force. I don't know that force. I'm representing by your F. So F will be proportional to this. Restoring force is directly proportional to your displacement. Removing this proportionality constant, we get some constant that is nothing but of your k into your x, and in opposite direction that is nothing but of your minus of your k. So this is your restoring force formula. F is equals to your minus of your k into your x part of relation. Clear for everyone?
Yes.
So what is a k here, beta? So k is right now for me some positive constant. This also you got in Hooke's law in elasticity, beta.
Yes.
In elasticity also we got F is equals to K into X. In springs also we got F is equals to K into your X. What is the K here? K is your positive constant, and we are calling that one as of your what? Force constant. We are calling that one as of your force constant. And what is an X, beta? X is your displacement from mean position. X is your displacement from your mean position. Mean position. What is the mean position, beta? This position is your mean position. Okay, na? This one is your mean position. This one is your mean position, and this one is what? Your extreme position. Okay, this one is your extreme position. This is mean position, this is extreme position. This restoring force is directly proportional to restoring force అవ్వచ్చు, లేకపోతే టార్క్ కూడా అవ్వచ్చు. So restoring force or torque acting on a particle is directly proportional to the displacement from your mean position. Displacement from your mean position, and is always directed where, beta? This is important. It is always directed towards where? Mean position. It is always directed towards mean positions. F is equals to minus of your k into x. K is your positive constant, which is called as of your force constant, and x is nothing but displacement from the mean position. What is this negative sign indicates, beta? Negative sign indicates. Can you tell me what is indicates,
Because
beta?
restoring force is coming
Yeah,
backwards.
it indicates that force is always directed. Force is always directed towards mean position. Towards mean position. Okay. Whatever assignments I'll be trying to send on this one, beta, we'll try to compulsorily discuss in the class also, beta. I'll give as of a working. And if you're not getting, you please let me know. I'll try to do every day. After the moment I complete this topic, I'll send you the assignments. And tomorrow, before I start the class, I'll be discussing that assignments better. Assignments practice and problem practice very much required for this topic. Okay, na? Okay, beta.
Yes.
So that is about your simple harmonic motion. If you have any doubt in this one, just see it better. No doubt on that.
No, sir.
Next one is types of SHM. Types of SHM. In our syllabus, we are having two types of your SHM, beta. The first one is known as of your linear SHM. The first one is known as of your linear simple harmonic motion. The next one is about your angular simple harmonic motion. First one is linear, and next one is about your angular. So let us first try to talk about your linear simple harmonic motion. Linear simple harmonic motion. What do you mean by linear, beta? What do you mean by linear? In the simple straight line. In the straight line, like say for example, like this, if I'm having the condition, like say this is your horizontal surface, and on this horizontal surface we are having a block. Okay, I'll take somewhere from here mean position. Okay, so this one is say for example of your point, this one is your mean position, this one is your mean position, like your home. isn't it? This is your
Yes.
mean position. Wherever you go from your home, again, you need to come back to the original position only. Like say from
Yes.
this mean position, this block has been gone to this distance on a straight line. So this is your
Yes.
block which is being gone in your straight line right now. So the displacement moved from here to here is right now, say for example of your x. And this is your right extreme. This is your right extreme position, isn't it? And this will be your left extreme position. This is your left extreme position, right? Okay. So when you're going from mean position to your extreme position, what is the necessary and sufficient condition for SHM beta? Can you tell me? The necessary and compulsory condition is force must be directly proportional to displacement, but in the opposite direction. So I can write here necessary and sufficient condition and sufficient condition necessary and sufficient condition for simple harmonic motion is f is equals to minus of your k into your x. F is equals to how much beta? F is equals to your minus of your k into your x part of relation. What is F here? Restoring force. X is a displacement from the mean position and K is your positive constant called as a what beta? Force constant part of relation. Is it clear?
Yes.
So if I write this one mathematically, see how I'm writing very carefully. F is equals to minus of K into your X. This force can I write in terms of mass and acceleration beta. So it
Yes.
is mass into acceleration is equals to minus of K into your X. Can I write the acceleration in terms of displacement beta? Double differentiation. Am into your d square x by your dt square is equals to minus of k into your x. Everything I got in terms of x now. Have you got this one? Actual, what is the formula for acceleration beta? Can you tell me what is the formula for acceleration? Actual formula for acceleration, a is equals to dv by dt, isn't
Yes.
it? So it is equals to d by your dt. How do you write velocity? Velocity is equals to dx by dt, kada?
Okay. Yes. Yes.
So this will be equal to what? D square x by your dt square, kada?
Yes. Sir.
So from there, I got this value. Is it clear?
Okay. Yes. Sir.
Now, see, if I take this value here right now, I can write this one, you see, d square x by your dt square is equals to minus of your k by your am into your x. Can I write like this? I'm taking this m this side. This minus also you take inside. So this one is d square x by your dt square plus of your k by your m into your x is equals to 0. Is it clear? Can I write like this?
Yes. Sir.
So this one is known as of your differential equation of SHM. This is known as of what? Differential equation of SHM. That means to identify whether the particle are making an SHM or not, we need to see that it is obeying this relation. That is d square x by dt square plus k by your m into your x is equals to your 0, is equals to your 0 part of relation. Is it clear?
Yes. Sir.
Is it clear?
Yes. Sir.
Okay, na? So that is about your differential equation. How much time is left out beta for the recording?
5 more. 5 minutes
So that
left.
was about your simple harmonic motion condition. Is it clear beta?
Yes. Sir.
So let's try to go for the next one right now. Okay, give me the graph for this one beta. F is equals to minus of k into x. Can you give the graph for this one?
Sir, minus k means like shall we take it in the negative x-axis only, sir?
Negative
Or
x
shall we
axis.
consider?
Yeah. See, y is equals to mx, we can complete it beta. We know the basic equation. F
Yes.
is equals to minus of k into your x. Compare with your straight line equation. Y is equals to your m into your x. On y-axis
Yes.
will take force, on x-axis will take your x. So
Yes.
if I'm taking the graph like this, On y-axis, what will be taking? Force. On x-axis, we are taking your x. Slope, there is no slope. But, sorry, there is no constant. Slope is what? Negative.
Yes, sir.
Slope is negative means what? It should be something like this. అంతే కదా?
Yes, sir.
Because if it is in second quadrant, then only slope will be negative kada. Because tan
Negative.
theta
Yes,
kada.
sir.
Slope is nothing but tan theta. Na?
Yes, sir.
So tan theta is right now in this given condition right now, isn't it? So here this force is F is equals to minus of your K into X. Is it clear?
Yes, sir.
Okay. So that was about your given condition right now. So that was the condition. We need to write the formula for that one. So force is equals to minus of K into X, where Y is equals to M into X if I'm comparing. So we are getting a straight line passing from your origin part of a relation. Is it clear?
Yes, sir.
Okay, chalo, fine. So let us now to go for the solution of your equation of SHM beta. How do we got the basic equation of your SHM part of relation? But before that, I need to give you one small formula related to your differentiation beta that and the integration part of relation, which we have been left out in the initial condition part. But that equation is very much required right now here. So can I give you that formula for you beta right now?
Yes.
Basic mathematics differentiation integration. I already told you right now, but there is one small formula which you need to remember how to differentiate the given condition in terms of your sign part of relation. We'll just write you that given condition, then we'll try to go for the next one. Okay, na? So just make here right now basic mathematics, basic maths. So this part of mathematics is compulsory required before we go for the derivation of the solution. That is differentiation of d by dx of your sine inverse of your x. Sine inverse of your x is equals to 1 by under root of 1 minus x square. Okay, na? This is the
Yes,
equation
sir.
which we need to remember. Second, you need to remember this one only. Whenever you get a differentiation of sine inverse of x, directly you write this one as how much beta? 1 by under root of 1 minus of your x square part of relation. The same way right now, differentiation of your d by dx of your tan inverse of your x, tan inverse of your x will be equal to 1 by 1 plus of your x square, 1 by 1 plus of your x square part of relation. In the same way, differentiation of d by dx of your secant inverse of your x, secant inverse of your x will be equal to 1 by x into under root of your x square minus 1. Okay, in this one, the first
Yes,
one
sir.
will be using right now in the derivation beta. You need to just remember this one. Okay, like differentiation of sine inverse of x is equals to 1 by under root of 1 minus of your x square. In the same way, integration if I am taking right now, in the same way, integral of your 1 by under root of your 1 minus of your x square into your dx will be equal to how much beta? Sine inverse of your x. Okay, just opposite the different integration. The same
Yes,
way, integral of 1 by 1 plus of your x square into your dx will be equal to your how much beta? Tan inverse of your x. And in the same way, integral of your 1 by x into under root of your x square minus of your 1 will be equal to your into your dx.
secant.
This one is
Secant.
nothing but of your secant inverse of x. So this is the basic maths you need to remember.
Yes. Sir, I'll
Okay,
rejoin, sir. Yes, sir.
అయిపోయిందా టైం అయిందా?
Yes, sir. I'll rejoin.
Okay, then I'll start tomorrow na beta, no problem కదా.
Okay, sir.
Bye.
Sir, an assignment you'll send me now.
I'll send you today right now. On in this introductory part, I'll send you right now. Then we'll try to discuss that one tomorrow. Okay?
Okay, sir.
Okay, chalo.
Thank you,
Bye
sir.
beta.
Bye,
And notes compulsory chadu nana.
sir. Yes, sir.
Compulsory you need to read the notes and try to make your concepts clear.
Okay, sir.
Okay, chalo. Bye beta.